to this summary video on 8.2 on the DP Physics program to do with thermal energy transfer. How can thermal energy be transferred? Either by conduction, convection, or radiation. Conduction happens in solids and is mainly due to lattice vibrations. Convection happens in liquids when hot air rises and cool liquid falls. However, radiation can happen in a vacuum, and it's the transfer of energy via EM radiation. You can stop and pause this video on this table if you want, which describes the differences between conduction, convection, and radiation. The main thing is that for radiation, we have a formula which we can calculate the radiated energy quite easily. We're going to go into that in more depth in the next slide. So Stefan Boltzmann's law tells us how much thermal energy is transferred per unit second, given the body's surface area A and its temperature to the power 4. Remember, temperature is the Kelvin temperature and is measured in Kelvin, not temperature measured in Celsius. However, little e, note, is this quantity called emissivity. If E is equal to 1, we call it a black body emitter, and it emits all the radiation that it has. If E is 0, then it will emit no thermal radiation. We can talk about a rate of energy transfer because at the same time as the body is emitting energy due to its temperature T, it's also absorbing energy from the surroundings due to the surrounding temperature Ts. So the net power radiation ends up to be E sigma A brackets its temperature to the power 4 minus the surrounding temperature to the power 4. And if we take our temperature of 36 degrees, that's our body temperature, minus the surrounding temperature of 20 degrees, times by a surface area of 1, we end up with a net power output of a human being on average to be about 100 watts. Wien's displacement's law tells us, given the peak wavelength, because as the peak wavelength decreases, the surface area increases. We know from Wien's law that the product of the peak wavelength and the Kelvin temperature is a constant 2.9 times 10 to the minus 3. Therefore, knowing the peak wavelength of the Sun to be 500 nanometers, we can work out the surface temperature of the Sun to be 480 Kelvin. These are spectra for black body radiators. The solar constant is the amount of intensity received at the Earth due to the Sun, and for the Sun's temperature, its power is it's a black body emitter. It emits power at this rate, 3.9 times 10 to the 26 watts, and at a distance of the Earth, we receive 3.9 times 10 to the 26 divided by 4 pi times this number here, which is the distance from the Sun to the Earth, squared, which gives us 1,400 watts per square meter, which is what we call the solar constant. Let's come up with an expression for the average intensity at the Earth's surface. So we have this radiation from the Sun, which at the Earth's surface has intensity S, or at this distance here. So the question is how much power is absorbed? Power is equal to intensity times by area. Now the area we see here is an area of the cross section of the Earth whose radius is r. So this will be the solar constant times by pi r squared, where r is the radius of the Earth. However, not all of this power is directly absorbed. Some of it is directly reflected back into space, because the Earth has something called an albedo, which is the scattered energy or scattered power over the total incident power. So what is actually absorbed is actually 1 minus alpha lots of this thing here. Now in order to find the intensity is power over divided by area, so this would be 1 minus alpha times s pi r squared divided by the whole surface area of the Earth in order to find what we call the night and day average. So this is divided by the area of the sphere, which is roughly 4 times 4 pi r squared. That's the surface area of the sphere, the same size as the Earth. So we see there's some things that cancel here. R squareds cancel, the pi's cancel, and if we plug in some values, the albedo of the Earth is roughly 0.3. This becomes 0.3 times 1400, which is the solar constant, divided by 4, which is roughly 245 watts per square meter. Now comes an important consequence, and that's the energy balance of the Earth, and this is without the greenhouse effect, and we'll actually see that some greenhouse effect is actually a good thing. So if we look at the simple energy balance model here, we have the energy or the incident intensity from the sun. Some of that is directly reflected through its albedo, or in fact alpha lots of I is directly reflected, which leaves that 1 minus alpha I is absorbed, and then when the system is in balance, 1 minus alpha lots of I then is re-radiated back to space. So in terms of the energy balance, we have to have the energy in equals the energy out, or the intensity in equals the intensity out. The intensity in we just found from the previous in the previous slide is 1 minus alpha s over 4, which is 245 watts per square meter. The intensity out is given by the Stefan-Boltzmann's law, emissivity times Stefan-Boltzmann's constant times the surface area times the absolute temperature to the power of 4 divided by the surface area of the body. So those two areas cancel, and we end up with 245 equals 5.67 times 10 to the minus 8 times t to the power 4, divide both sides by the constant and take the fourth root, gives us a temperature of 256 Kelvin, or minus 17 degrees Celsius. Therefore, if we had no atmosphere, no greenhouse effect, our planet would be a frosty minus 17 degrees Celsius, which is not conducive to life. However, with the greenhouse effect, you have a blanket of gases up in the atmosphere which absorb some of this re-radiated radiation and then radiate it back, well, in all directions, but some ends up going back down to the Earth, which means that there is more energy in than out, and you end up with an equilibrium temperature which is higher than negative 17 degrees Celsius, and which means that life can form. So the greenhouse effect is caused by these greenhouse gases: water, carbon dioxide, methane, and so on. And the energy is absorbed and re-radiated in all directions, some of which is being absorbed by the Earth, causing additional warming. That's the greenhouse effect. However, the enhanced greenhouse effect is the additional warming due to anthropogenic sources of greenhouse gases, i.e. humans burning fossil fuels, which is less good, because then that can heat up the planet to higher temperatures, which has some bad consequences.